Okay, now let's continue talking about the electromagnetic spectrum. Electromagnetic spectrum. It consists of electromagnetic waves. These waves consist of two types of waves. One of these is moving in vertical side like this, okay, in the vertical plane. The other one moves horizontally. So we have two types of waves, okay, one moving horizontally and the other vertically, okay. One of these is electrical wave, the other is mechanical wave. Okay, the electromagnetic waves have the same speed in air or vacuum, which is 3 times 10 to the power 8 meters per second. And we have many types of electromagnetic waves. The electromagnetic waves consist of a big family. Let's start by this. The visible region, okay, and we have infrared. On the other side we have ultraviolet. So here we have 7 colors, which are red, orange, yellow, green, blue, indigo, and violet. Roy G. Bev. Okay, now here we have X-ray and gamma ray. On the other side we have micro and radio wave. As you move towards the gamma side, frequency of the wave increase, wavelength decrease. But all of these have the same speed, which is 3 times 10 to the power 8 meters per second. You have to remember the wavelength or the range of wavelengths for each type of wave, okay? Maybe sometimes there is an intersection between X and gamma for the wavelength and between micro and radio waves. You have to remember this table very well. This is the wavelength for each radiation. You have to memorize this very well, okay? So this table, you have to remember it very, very well. You can see here X-ray and gamma, there is an intersection between these, so you can't recognize if the wave is gamma or X-ray only if you know from where this radiation comes. And here the microwave and infrared, there is an intersection between these two rays. So you have to know from where this radiation comes, okay? Here we have the radio wave, okay? And as you go to the right side, frequency increase. By this, we finish chapter 14. Now, let's start with chapter 15, which is talking about superposition. If two waves superimpose together, or interference, if two waves met together, okay? This is wave and this is the other wave and they met. There is an interference between these waves. Here we have two sources of wave. So this wave 1 and this wave 2, we can see the interaction between these waves. We can see here that there is a point of intersection of two waves. Here, this is the wave number 1 from this source. I make it green. And this is wave number 2 and wave number 3. These are the crests of the waves. Now let's take another color. We have, this is the second source, and this is the wave number 1, and here wave number 2, and a third wave. Okay, now we see here that this point is an intersection, and this wave is intersection, or this point, and here another intersection. So all of these points in this line, okay, are coming from maximum displacements. Okay, what is the maximum displacement here? That the crest and the crest are met together. Okay, here again we have crest and the crest. Okay, and here again we have intersection from the two waves. So these lines are the lines of maximum displacement. We have a crest met with a crest, or a trough met with a trough from wave number 1 and wave number 2. Okay, so if we have a crest met with a crest, or a trough met with a trough, so we have a constructive interference. Okay, this is a constructive interference when two waves met together, have the same frequency, so you add up the displacement together like this, you have a big wave. Okay, this value equal the summation of this amplitude and this amplitude. Okay, crest crest, we have a big crest, trough we have a big trough. This is a type of interference which is a constructive interference. As seen here, we have this line, the line of maximum displacement, which is a constructive interference. Okay, between these we can see the destructive interference here and here. These are the destructive interference when a crest met with a trough, crest from wave number 1 with a trough with wave number 2. If we have crest and trough like this, this is wave number 1, and wave number 2 is in the opposite direction, so the total may be equal 0 if this displacement equal this. Okay, now here we have two waves, this wave number 1 and wave number 2, and these waves have same amplitude as shown here, and the waves are moving in phase. So when these waves meet, there is a constructive interference. So the summation of the amplitude give us a big amplitude. We have 2A. Okay, if the two waves are in phase with a phase difference of by radian or 180, the peak of one wave arrive at the same time as the trough from the other, and they will interfere destructively. So we have two types of interference: constructive and destructive. If we have this wave number 1 and wave number 2, these are moving in phase, it is a constructive interference. This is the total. And if we have 180 degree between the two waves, so we have a destructive interference. The total is 0. We have many types of constructive interference. Maybe this is wave number 1, okay, and here we have, let's say, wave number 2. It's like this. Okay, so what we can do, we will add this value and with the amplitude here. So this is the total here, and this here the total, here 0, and this is the maximum point. So you add 0 plus this displacement, and so on. So maybe you have a wave like this. Maybe this is the total wave of the two waves. Okay? You can see many different waves. Now, if we have this wave number 1, and let's say this is wave number 2. Now, the total wave will be like this. Okay, we add these displacement together, and this is the total of the wave. Now, so we have constructive and destructive interference. We see here the constructive interference. It is the total of the two waves. And here the destructive interference. We have two waves in opposite directions, so the total is 0 if the amplitudes are the same. If the amplitude in the upper part larger than this amplitude, maybe we have smaller wave here. Okay, so this is the situation of an example of a principle of superposition of the wave. Superposition of the wave. The principle of superposition states that when two or more waves meet at the point, the resultant displacement of that point is equal to the sum of displacement of the individual waves at that point. It is the total of the two waves. So we have to be careful about the direction of the waves, about the phase difference between the two waves. Now, if we have two sources of light, this is source number 1 and source number 2, and the sources are coherent. Coherent means they have the same wavelength, same frequency, same amplitude, okay? Same wave. And the rays go from this and from this, and they meet at this point, okay? And maybe they meet at the center, or maybe they meet at this point, okay? So depending on the path difference, we can see if the screen here show a bright point or a dark point, okay? So if we have, again, this graph, we have two sources of light, okay? And this is the center, and this is the screen. What we will see on the screen, we will see a place which is bright here at the middle between these 2 points, and then there is a dark and bright again, dark and bright again, and dark, and so on. And the same thing on the other side, okay? And the distance between the center of bright to the center of the bright equal to the distance between center of the dark and the center of the dark. Now, if we have source of light here, and this is the other source, this is ray from here, and this is the ray from here, the distance traveled by this and this have the same value. So the difference in the distance traveled equal 0 between these two rays. So we can say that the path difference is 0. So when the path difference is 0, so we have constructive interference. There is a bright region here, okay? The same thing if we take this point, this is the ray number 1, and this is the second ray. Now, if this ray travel distance larger than the distance of ray number 1 by wavelength or double wavelength or triple wavelength, any integer number multiplied by wavelength, so we have a constructive interference. Since this is the second bright region, so here the distance is 2 lambda, okay? This is a constructive interference. If we talk about this, the difference is 1 lambda, 1 wavelength, okay? If the difference 1 lambda or 2 lambda or 3 lambda and so on, we have a constructive interference. Okay, what about the points in between? Here we have the first ray and this is the second ray. Now, the difference between the first and second ray is lambda over 2, okay, which is half wavelength. So here we will have a dark region because the difference is lambda over 2. Here we have a dark region again because the difference is 3 lambda over 2 and so on. The same thing happened on the other side. So we have a bright and dark depending on the path difference or the phase difference, okay? Here path difference is wavelength, so bright, path difference 0, bright, path difference lambda over 2, so it is dark region, here dark and here bright, okay? So there is a path difference between the waves arriving D if the whole number of the wavelength lambda 2, 3, etc. the waves arrive in phase and interference constructively, because you can see this is the wave number 1 and the wave number 2, both of these met by the same shape, so it's a constructive interference. Here you can see there is a crest from wave 1 with a trough from wave 2, so we have destructive interference. So if the difference lambda over 2, 3 lambda, 5 lambda over 2, etc., the interference is a destructive interference. The equivalence to the phase difference between the waves pi, 3 pi, 5 pi, etc. This is a constructive interference, okay? And the wave cooled interference pattern, one is shown in figure 15.2. The same thing happened with a sound wave. If we have two speakers here and we have student pass like this, he will hear in some places a loud sound, here again loud sound, here it's quieter, and here it's quieter, and here it's quieter, okay? Because here we have a constructive interference and we have a destructive interference in other places. Okay, so what happened in the light is the same as what happened in the sound. Here we have another two sources of light, okay, the car heading. We can see this is light from the first one and this light for the second one. Here is the region of interference. Here we will see the interference. The light here is not the same at all points, okay? So to produce an observable interference pattern, the two wave source must have the same single frequency, not mixture of frequencies. Because of that, we need these lights to be coherent. They must also have constant phase relationship. In the sound experiment, the waves from two loudspeakers have the same frequency. Why? Because they start from the same generator. So the wave source which maintain coherent phase relationship are described as coherent sources. These are coherent sources. Now we have here, this is wave number 1 and this is the second wave. These waves are move in the same direction and we can see that these waves are in opposite direction. So if these waves met in this shape, there is a destructive interference between these, but here we have a constructive interference because they have the same phase difference. Okay, so if the path difference between the waves 0, lambda, 2 lambda, we have a constructive interference. Okay, remember this very well. Okay, we'll stop here now.